In this lecture, we will discuss about important specification criteria, sensitivity analysis, use of proxy variable, use of lag dependent variable, the concept of measurement error of both the dependent variable as well as the explanatory variable, the criteria of goodness of fit of the model like Akaike information criteria and Schwarz Bayesian criteria, and HAUSMAN'S test for endogeneity. In this lecture, we will start our discussion by some important specification criteria. We can summarize the previous discussion into 4 criteria to help to decide whether a given variable belongs to the equation. First of all, we have some suggestion from economic theory. Is the variable placed in the equation and unambiguous and theoretically sound? Then we have to go for t-test. Is the variable estimated coefficient significant in the expected direction? Third, you have the measure of adjusted R square. Does the overall fit of the equation adjusted for degrees of freedom improve when the variable is added to the equation? And finally, regarding bias, do other variables' coefficient change significantly when the variable is added to the equation? If all these conditions hold, the variable belongs to the equation, and if none of them hold, it does not belong to that equation. The tricky part is the intermediate cases, which uses sound judgment, and almost any result can be obtained from a specification database by simply specifying different regression until estimated or estimates with desired properties are obtained. Hence, the integrity of all the empirical work is open to question. To counter this, the following three points of best practices in specification searches are suggested. Rely on the theory rather than statistical fit as much as possible when choosing about the variable, functional form and the like. Then minimize the number of equations estimated except for the sensitivity analysis that will be discussed later in this section. Thirdly, reveal in a footnote or appendix all the alternative specifications that are estimated. Now, contrary to the advice of estimating few equations as possible and based on the theory rather than fit, sometimes we use journal article where author listing result from 5 or more specification. What's going on here? In almost every cases, the author have employed a technique called sensitivity analysis. The analysis consists of purposely running a number of alternative specifications to determine whether particular results are robust, not statistical flukes to a change in specification. Why this kind of analysis is useful? Because true specification is not known, and data mining involves exploring a data set and to try to uncover empirical irregularities that can inform from economic theory. That is, the role of data mining is opposite to that of traditional econometrics, which instead tests the economic theory on a data set. But be careful, a hypothesis developed using data mining technique must be tested on a different data set or in a different context than the one used to develop the hypothesis. And not doing so would be highly unethical. After all, the researcher already knows ahead of time what the result will be. Similarly, you can use the proxy variable because if the model is misspecified, because no data set are available on an important variable x, then it may be possible to avoid the omitted variable bias by using a proxy variable. A proxy variable must be related to the unobservable variable. For example, if x3 star is the proxy variable, then x3 star can be made a function of delta naught plus delta 3 x3 plus v3, where star implies the unobserved case. Now suppose we just substitute x3 for x3 star. So what do we need for this solution to give us the consistent estimate of beta 1 and beta 2? Now expected value of x3 star given x1, x2, x3 is equal to expected value of x3 star given x3, and which is equal to delta naught plus delta 3 x3. That is, u is uncorrelated with x1 and x2 and x3 star, and v3 is also uncorrelated with x1, x2 and x3. So we are really running a regression y equal to beta naught plus beta 3 delta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 beta 3 delta 3 x3 plus u plus beta 3 v3, and have just redefined the intercept error term x3 coefficient. But one can end up with biased estimate, say x3 star equal to delta naught plus delta 1 x1 plus delta 2 x2 plus delta 3 x3 plus b3. Then really running y is equal to beta naught plus beta 3 delta naught plus beta 1 plus beta 3 delta 1 x1 plus beta 2 plus beta 3 delta 2 x2 plus beta 3 x delta 3 x3 plus u plus beta 3 v3 will mean the bias regression, and bias will depend on the sign of beta 3 and delta 1, and this bias may still be smaller than the omitted variable bias. So by using proxy variable, you will be able to reduce the extent of omitted variable bias. Similarly, you can use the lag dependent variable. So what if there are unobservable variable and you can't find reasonable proxy variable? So in this case, it may be possible to include lag dependent variable to account for omitted variable that contribute to past and current value of y. Obviously, you must think of past and current y that are related to this variable, and it will make some sense. Now we will discuss the concept of measurement error. Measurement error can arise both in the case of dependent variable as well as explanatory variable. So let me start with the discussion of measurement error in a dependent variable. Define measurement error as E naught equal to y minus y star. Thus really estimating y equal to beta naught plus beta 1 x1 up to beta k xk plus u plus E naught. When will OLS produce unbiased result? If we find that E naught and xj and u are uncorrelated, is unbiased, and if expectation of E naught is not equal to 0, then beta naught will be biased, though while unbiased, larger variances than with no measurement error. Now let us then discuss the measurement error in the case of explanatory variable. Define measurement error as E1 equal to x1 minus x1 star. Now assume expectation of E1 equal to 0 and expected value of y given x1 star and x1 is equal to the expected value of y given x1 star. Then really estimating y equal to beta naught plus beta 1 x1 plus u minus beta 1 e1. The effect of measurement error on OLS estimate depends on our assumption about the correlation between e1 and x1. Suppose covariance between x and e1 equal to 0. Now in this case OLS remain unbiased and variance will be larger. Now suppose covariance of x1 star and e1 equal to 0, which is known as classical error in variable assumption, and then covariance of x1 e1 equal to expectation of x1 e1 equal to expectation of x1 star e1 plus expectation of e1 square, and which is equal to 0 plus sigma e square. In this case, x1 is correlated with the error, so estimates are biased. And if we take plim of beta 1 hat, it will be equal to the true value beta 1 plus covariance between x and u minus b beta 1 e1 divided by variance of x1. So this is equal to beta 1 minus beta 1 sigma e square divided by sigma x star square plus sigma e square. Now notice that the multiplicative error is just the variance of x1 star by variance of x1. Now since variance of x1 star divided by variance of x1 is less than unity, the estimate is biased towards 0, and which is called the attenuation bias. It is more complicated than with a multiple regression, but it can still expect attenuation bias with classical error in variable. Now finally we will discuss two goodness of fit criteria. One is Akaike information criteria and the other is Schwarz Bayesian criteria. These measures takes into account goodness of fit and rewards parsimony for simplicity. The BIC criteria places a higher penalty on using degrees of freedom. Now let us start my discussion with Akaike information criteria. Suppose that we have a statistical model of some data and let L be the maximum value of the likelihood function for the model and let K be the number of estimated parameters in the model. Then AIC, that is the value of the model, is the following. AIC equal to 2K minus 2 log of L. Given the set of candidate model for the data, the preferred model is the one with minimum AIC value. So we will choose that model for which the Akaike information criteria will be less. Hence, Akaike information rewards goodness of fit as assessed by the likelihood function, but it also includes penalty, that is an increasing function of the number of estimates of the parameter. So you find that as K increases, then Akaike information criteria increases, and if this is so, we will not choose that model for which Akaike information criteria has increased due to inclusion of more explanatory variable. Now the penalty discourages overfitting, increase the number of parameters in the model, almost always improves the goodness of fit. Now let us then discuss BIC. BIC is formally defined as BIC equal to minus 2 times log L hat plus K times log N, where X is the observed data, theta is the parameters of the model, N is the number of sample data point in the X, a number of observations, equivalently the sample size. K is the number of free parameter to be estimated. If model under consideration is a linear regression, K is the number of regressions including the intercept. L hat is the maximized value of the likelihood function of the model. That is, L hat equal to P times X given theta hat M, where theta hat are the parameter value that maximize the likelihood function. The BIC is an asymptotic result derived under the assumption that data distribution is an exponential family, that is the integral of the likelihood function Px given theta m times the prior probability distribution P theta m over the parameter theta of the model for fixed observed data x is approximated as -2 times log of p x given m, which is exactly equal to BIC, and which is equal to -2 times log L hat plus k times log of n minus log of 2 pi. For large n, this can be approximated by the formula given above. The BIC is used in model selection problem where adding a constant to BIC does not change the result. In the next step, we will discuss Hausmann's test for endogeneity. Consider the linear model y equal to x beta plus e, where y is the dependent variable and x is the vector of regressions, b is a vector of the coefficient, and e is the error term. We have two estimators for b, b0 and b1. Under the null hypothesis, both of the estimators are consistent, and but b1 is inefficient, has smallest asymptotic variance at least in the class of the estimator containing b0. Under the alternative hypothesis, b0 is consistent whereas b1 is not. Then Hausmann statistics is defined as H, which is equal to B1 minus B0 prime divided by variance B0 minus variance of B1 whole inverse multiplied by B1 minus B0, where plus denotes the Moore-Penrose pseudo inverse. Under the null hypothesis, these statistics has asymptotically the chi-square distribution with the number of degrees of freedom equal to the rank of the matrix variance of B0 minus B1. If we reject the null hypothesis, it basically implies that B1 is inconsistent. This test can be used to check for the endogeneity of the variable by comparing instrumental variable IV estimates to the ordinary least square variable estimate. It can be used to check the validity of the extra instrument by comparing instrumental variable estimate using a full set of instruments Z to instrumental variable estimate that uses a proper subset of Z. Note that in order to do the test to work, in the latter case, we must certain of the validity of the subset of Z, and that subset must have enough instrument to identify the parameter of the equation. So, what we need in the subset, we must have enough instrument available in order to identify the parameters. Now, Hausmann test, Hausmann also showed that the covariance between the efficient estimator and the difference of an efficient estimate and an inefficient estimate is 0. Now, there is an omitted variable interpretation of Hausmann test. There is an alternative way of implementing the Hausmann test, returning to the equation y equal to bx plus e. Now, let us denote x hat the predicted value of x and r hat be the estimated residual, that is r hat equal to x minus x hat. Then the estimated equation y equal to beta x plus c x hat plus u, or y equal to bx plus cx hat plus w, using OLS and test the hypothesis c equal to 0. These equations are expanded regression and the test is identically the same as based on H statistics as mentioned earlier. So, in the omitted variable interpretation of the Hausmann test, what we do, we first find the expected value of x. Now, then we use the expected value of x as an additional explanatory variable in the original regression, and if we find that c is equal to 0, then we say that there is no omitted variable case. The omitted variable interpretation enables us to generalize the test to the case where we have more variable whose endogeneity we are interested in testing. Suppose that one of the equation in a simultaneous equation model is y1 equal to b2y2 plus b3y3 plus a1z1 plus e1, and we want to test the hypothesis that y2 and y3 are exogenous, that is independent of e1, the alternative hypothesis being that they are not, and it is assumed that the variable z1 is exogenous. Then to apply HAUSMAN'S test, we estimate the expanded regression y1 equal to b2y2 plus b3y3 plus a1z1 plus c2y2 hat plus c3y3 hat plus e1. Now let us define r2 hat equal to the difference between y2 and y2 hat, that is r2 hat shows the estimated residual for the variable y2. Similarly, R3 hat is defined as y3 minus y3 hat, where R3 hat shows the difference between the actual value and estimated value for the explanatory variable y3. We then estimate the model y1 equal to b2y2 plus b3y3 plus a1z1 plus c2 r2 hat plus c3 r3 hat plus u2, and test the hypothesis that C2 and C3 are equal to 0. Now, if we find that C2 and C3 equal to 0, then we claim that there is no misspecification as suggested by the test. In this lecture, we have discussed about important specification criteria, sensitivity analysis, use of proxy variable, use of lag dependent variable, measurement error of both the dependent as well as explanatory variable, the criteria for goodness of fit of the model like Akaike information criteria and Schwarz Bayesian criteria, and also HAUSMAN'S test for endogeneity.